program. Of course, my special thanks go to Dario, who is actually the person who really did almost all the work. So thank you, Dario. So my, let's say, minimal contribution here is to at least to give you some encouragement at the end of this, sorry, at the beginning of the, maybe at the end as well. For the beginning of this program, some encouragement to tell you some basic things that usually are always somehow behind the words, the sentences that you read in papers, typically introductions, like you read like Eigenstate Thermalization hypothesis, it's a mechanism for thermalization, period, and some citations. And then if you are a newcomer and you don't know what does actually mean, then you are afraid to ask, and nobody explains you, and then you may be frustrated. Hopefully not, but the purpose of this lecture is just to give you really some basic introduction that is meant for young people to ask questions and to really provide some minimal background that I guess you will need throughout this workshop. Now, as you have seen on the program, there are like 2 hours today and 2 hours tomorrow. I will talk for 45 minutes and then we'll do a break and then another 45 minutes. Please interrupt me anytime. So the plan of this lecture is to start first with slides, maybe for 10 minutes or so, and then I will go to Blackboard, and I will try to give you a basic course on eigenstate thermalization hypothesis and quantum thermalization. Now, the plan of my personal plan that I will pursue is that I will try to go today over the entire program that I want to share with you without too much details. And then tomorrow I will go again through with a bit more details. Okay, the level of details will also depend on your interests or maybe your suggestions after the lecture. If you have some particular ideas or particular wishes, just let me know, and then we can maybe discuss that next day. Okay, so I repeat, you are free to ask anytime, and this is why I'm here. This is the purpose of this lecture. Now, let me start with something simple. So, okay, let's see if that works. Not working. Oh, no, it doesn't work.
Try to.
Yeah, that works. Okay, sure. Okay, so what is your first impression or first thought when we talk about thermalization? Let's first stick for a few minutes just to classical world. These are typical examples you can see maybe in other lectures as well. We know that if we bring something far from equilibrium, likely it will relax back to equilibrium. This is our everyday experience. Well, it's my first time now on the southern hemisphere, so now we have summer in Europe. That's why I brought that here. It's like spring or winter time, but this is what happened to us often now in summer. Now, okay, this is a typical example that of course, in particular, kids like a lot. Now, another maybe even better example is from the classical world is the case that everyone is familiar with, that uses perfume. So when you spray perfume, it smells. So that's a good experiment because your nose is like it's a good tool for making observations. So you smell perfume, and then after some time, as you know very well, the perfume dissolves. I mean, you don't smell it anymore. So what is the mechanism behind? Of course, this gas has thermalized in the entire room. So let's consider this room as an isolated system. And if this is an isolated system, then at the end it becomes so diluted that we don't smell it anymore, right? So that's again an example of far from equilibrium setup, where far from equilibrium means that this nice smell is if I spray it here, it has high density around our nose. Okay, now I will talk mostly about thermalization. Now, also from time to time, I will use the word ergodicity. Now with ergodicity already, that's a term we have to be a bit careful about, because I'm not mathematician. I'm just theoretical physicist. So for me, definition of ergodicity is maybe different from ergodicity in the classical, in the mathematical literature. For me, ergodicity simply means that the long-time average or the long-time value of observable matches statistical ensemble prediction. This is what is for me ergodic behavior. But at the end of the day, I will define then later more sharply what do I have in mind with thermalization. So when do I say that that a given system thermalizes? Okay, now my main interest is in the quantum world. What is a true challenge in quantum world? Physics is experimental science, so the challenge is that if we want to address the question of thermalization of a given system, we have to first isolate it from environment. I think we all expect that if a system is coupled to environment, then you go back to Boltzmann and you go to statistical physics that we all know very well. But even when I'm not that old, but when I was younger, it was not that obvious answer to the question whether an isolated quantum system, even though it has many degrees of freedom, still can thermalize. Because when I was a PhD student like you, many senior people approach me and say, well, that will never happen. It will just oscillate forever. You have unitary time evolution, so why should it thermalize? And of course, from experimental point of view, that's a hard question, because first you have to really you have to make sure that your system is isolated for environment. But nevertheless, nowadays that can be achieved. That can be achieved in many experiments around the world. So let me just give you a few examples, just few of them. Of course, there are many more, but let me give you just some milestones in experimental activities. So one of the milestones was this experiment carried out in Munich now 13 years ago. It's a rather simple experiment, but and also the outcome is not surprising, but still it's good to show that such cases exist. So here the preparation is very simple. It's a lattice. These are ultra-cold atoms in optical lattices. It's a lattice, and what was the innovation at that time is that they really prepared a state that has a density wave pattern. So occupied, empty, occupied, empty, occupied, empty, and so on. So periodic pattern. And so moreover, what they could measure is actually was the occupation of this size, or the differences of the occupation, something that then later they in their follow-up experiments they could measure, the so-called imbalance. But here, if you just follow the occupation on some sides, let's say the odd sides, you see that initially it's empty, and then it goes to something which is 1/2. So in average, when system approaches thermal equilibrium, then it should forget information about the initial state. Of course, information about the initial state is that some sides are empty initially, right? But that's not the property of the thermal equilibrium. So at least to show that there's thermalization going on in this system, that has to go to something that is well understood. It's 1/2. Okay, that's a very simple example. But of course, at that time, it was important to demonstrate that is possible to measure. Now, another also well-known example, now 9-year-old, is from Harvard, from I think that is Greiner group, where they considered only few ultra-cold bosons in optical lattices, but still that was good enough to show that these interacting bosons on optical lattices, that first they can really make experiments such that these bosons evolve in isolation from environment. And this is shown in this figure where they measure the purity. So that is trace of rho squared. That's the purity of the global state. And if you see the purity here is, well, nearly independent on time. So it means that the system is to a good approximation really isolated from environment, at least for the time scale of the experiment. And then another thing is that if the system was prepared first in some initial state with a sharp occupation of boson, one boson per site, then after some time, actually this the system, the reduced density matrix effectively became mixed, so that all occupations are possible and so on. So that really the reduced state is close to even though the global state is pure, the reduced density matrix at a given site is close to thermal density matrix. That's something that was also important to see, that this good degree of isolation from environment is indeed possible nowadays. Now here I have shown you so far 2 examples where actually the outcomes at the end were not that surprising from the physical point of view, yet it was important to show technological advances that one can really realize that experimentally and measure. Now, on the other hand, there was even earlier experiment that I should also highlight here, and this is the so-called quantum Newton's cradle experiment carried out at Dave Weiss' group, that Dave should also come here at some point next week, and carried out at Penn State. Of course, that's just a sketch. It's again a quantum experiment, but this is a sketch of some one-dimensional gas of interacting bosons. So you should imagine that each ball here is an ultra-cold boson confined to one dimension. Here, actually, there's no lattice here. So if for those of you who think in terms of modeling, that can be described, for example, by the Lieb-Liniger model. But that's not so important. The important thing is that one-dimensional bosons with delta-like interaction actually are integrable, or at least in experiment they are close to integrable limit. And now this is now the challenge for theories, because if we now say the magic word of integrable or let's say localized or something that is different from thermal, then one can ask, well, are there some manifestations of this, some measurable manifestations of this phenomena that can be shown to be different from generic thermal behavior, something different from what I have shown before? And the answer is, of course, yes. And this was the kind of the important aspect of this experiment. You see, 2006, this is already now quite old. It's 19 years old. That was one of the first experiments to really show quantum coherent dynamics of an interacting system, well isolated from environment. So this not working again. So this figure is very famous from this experiment to show that actually this is somehow the corresponds to the density distribution, when actually these atoms were kicked in two opposite directions, having two different momenta and then colliding. That's why it's called quantum Newton's cradle. So of course the purpose of this cartoon was, you know, to be appealing to a broad audience and to show quantum coherence on a short time scales. Nevertheless, and as I said, that was one of the first experiments. It was probably not the first really experiment on non-equilibrium dynamics of quantum many-body systems. There was this collapse and revival experiment by Emanuel Bloch and Greiner and Hensch and I think Esslinger even earlier, when they quenched from the Bose-Einstein condensate to the Mott limit. That was probably earlier, but that experiment was important not because of this figure, which is the nicest figure in the paper, but because of that figure. That figure showed what happens after many collisions, right? This is just short times and just few oscillations. But after a long time, actually, the system has equilibrated. So I will refer to equilibration as an important phenomenon, and I will define it later what I have in mind. Of course, you can already understand equilibration means that actually there are no oscillations on top of this steady quasi-stationary distribution. But on top of that, this quasi-stationary distribution of velocities, that is for different interactions of bosons. That's not the important part for you now to understand. But the only thing that you can here guess is that this is non-thermal, looks non-thermal. Thermal would be something like Gaussian, something featureless. But if you see here many peaks, of course, these two side peaks are memory of the initial state, right? The initial state had kicks in two opposite directions. So initial state has sharp peak here, but after a long time, the system has equilibrated, but has not forgotten information about the initial state, right? And of course, this information about the initial state is a manifestation of absence of thermalization. Right? Now, to be very strict, to be very fair, this is still not exactly at the integrable limit, but close to integrable limit, because it's a real experiment that has other terms in the model that break integrability and so on. So if one waits for a sufficiently long time, they would eventually thermalize. These peaks would eventually go away, but probably it's hard experimentally to keep the system in isolation for such a long time. But the important thing is that the system has equilibrated, right? But still the kind of the quasi-steady state value, or the quasi-steady state distribution, is not thermal. Okay, so why is this experiment important? To just be aware that not any system may thermalize. Some of them may not thermalize, at least on experimentally relevant timescales. And all these discussion that we are gonna that will follow now here has to kind of take this into account, right? So when we understand thermalization, at the same time we also want to understand counterexamples to thermalization, or what are the conditions for an isolated quantum system to thermalize. Okay. Now, this was experimental input to the subject. Now, the rest of the lecture will be theoretical. So now you can ask, so is this, what do we know about quantum system thermalizing? And then what is the knowledge that we built on nowadays? Now, I will give you just a very brief and incomplete historical overview of the subject, just to get some flavor. I will not discuss now the content in details. I will just highlight some important keywords, key contributions, and then I will go to the main subject of the lecture, which will be presented on the whiteboard. Now, early considerations when we talk about quantum thermalization, as many of you associate now, we celebrate 100 years of quantum mechanics. And as you can imagine, actually the early questions were already posed very early as 1929 by von Neumann. And actually, it's not surprising, to be honest, because those of you who may have participated in some outreach events this year in celebrating 100 years of quantum mechanics may have realized how much of the work has been done just after 1925. So, for example, if you read the Nobel lecture by Heisenberg, I think it was 1933, at least when I read it again this year, I was surprised to see actually how much knowledge even about many-body physics, many-body quantum dynamics is already kind of envisioned there. So
how few we did.
Yes. Yeah, so in this narrow time interval between 25 until 30 or 33 or so on, many important questions were raised. Of course, this is one of the important questions that was raised. At that time, there were no experiments, of course, and then some of the works were forgotten or then revived after some time. But so von Neumann had this paper in 1925, essentially saying that for typical observables in typical systems, after sufficiently long time, the wave function, the information in this wave function for given set of observables will be essentially indistinguishable from microcanonical exploitation value. Of course, here you have to understand that at that time there was no, von Neumann didn't think about integrability or whatever special cases. So it's always this language of typicality, typical observable, typical Hamiltonian, and so on. And then you can prove certain statements. Now, of course, here I have to be honest and careful in the language that I'm using. I may use the word proof from time to time, but actually this proof is always, at least for me, it's a physicist proof, right? Nothing is rigorous that I will talk about. Even though it's nice to have proof, it's nice to have some derivations. I will try to follow also this logic, but nothing is very rigorous. Even actually this proof by von Neumann also has some, let's say, assumptions or physical assumptions inside that may be valid or may not be valid. And then later many people revisited that. For example, there's this paper by Markus Rigol and Mark Studnicki actually arguing that, well, this quantum ergodic theorem by von Neumann relies on the assumption that is essentially equivalent to ETH, right? So some, or maybe you can say some sort of typicality of states is assumed, so that you can at the end then say, well, I have proven that most systems will thermalize. Right? This is the logic. I'm highlighting that just to understand the logic. Here, most things that I will discuss actually have no proof. And ETH as such, as you can understand from the name, is Eigenstate Thermalization hypothesis. So it's a hypothesis. It's not a rigorous statement. And apart from some very special limits, we are not aware of any proofs, right? But under certain assumptions, you can then derive things and so on. So now, this is, of course, one of the early works. Now, some people also highlight that even if you open Landau-Lifshitz book on quantum mechanics, there is some footnote that actually agreement with statistical mechanics should, agreement with statistical physics should, in quantum world, also happen on a level of wave function, right? So even Landau and Lifshitz, I guess, at least on an intuitive level, had similar understanding that we now may call eigenstate thermalization hypothesis. Now, another important milestone was here happened in 1977 was introduced by Michael Berry, where he made again an important statement here, highlighted here in red, that essentially if one talks about system motion that is not regular, right? So whatever that means for us, because he didn't really study qubits on a lattice, but essentially the idea is that once we go away from the regular limit, let's say integrable limit, then the new state, the new stationary state, let's say the new wave function, the new eigenfunction, can be seen as a essentially random superposition of plane waves, right? Or something that has a random coefficients in a given basis, in a given simple basis. That is nowadays called Barry's conjecture. And Barry's conjecture is something that was very inspiring then for later work that I will also refer to. Now, another influential work on eigenstate thermalization, this is usually how we cite, how we refer to the literature, was made by Deutsch actually in 91, even though, as you can see here, that was completed in 89, but okay, I don't know the details behind. But the point is that here actually he realized very explicitly, so when you read the paper, it's there are not many formulas, but the text is very clear. So he essentially what he considered is a system that is, you can call it integrable, and then the perturbation that he considered to integrable system was essentially a random matrix. And when you perturb integrable system by a random matrix, essentially what he argued is that in some sense, as Barry envisioned already, is that the new eigenstates will be random superpositions in a given energy shell, will be random superpositions of these eigenstates of the regular or integrable system. Now he also actually has foreseen something that we now know. It's part of ETH, and this is that the fluctuations of the expectation values with respect to the microcanonical results will be very small, exponentially small in insistence size, and this is something now that it's important ingredient of the ETH that I will make more quantitative later. Well, after Deutsch, there was this paper by Mark Schwednicki in 94 that was actually even more influential. In particular, he introduced here explicitly the name of the phenomenon eigenstate thermalization. And essentially what he built on was again, the Barry conjecture. So he made it explicit that energy eigenfunctions behave as if they were Gaussian random variables for a given let's say, thermalizing system. Now, there is something that I will just briefly address in this lecture. I will not go too much into details, and this is also the word chaos, right? In principle, in jargon, we say if the system is chaotic, if the system is chaotic, then it thermalizes. Well, I would just talk about thermalization. I will not really refer to chaos a lot in this talk because different interpretations are also possible. You can also understand some systems to behave chaotically without thermalizing, but I will not go into these details. Okay, now actually the key contribution by Schwednicki that we are now all referring to is his famous ansatz for the matrix elements of observables in energy eigenstates, which is now called actually the ETH ansatz. So this is something that actually that was then introduced later in 1999 in this work, and this is something I will refer to throughout these lectures. I will comment in more details what actually this means, but essentially just to set the language. So the ETH ansatz for the matrix elements of observable, or Schwednicki ansatz, it's something that has the same meaning for the purpose of this lecture. Okay, and then finally here I will stop, because then this was also a very important work by Rigol, Dunko, and Olshani, essentially recognizing that all these considerations that were previously more phrased in let's say, more language of mathematical physics, or let's say in systems that are less interested to experiments, is actually relevant for the overwhelming majority of systems we are interested in, for example, in condensed matter or elsewhere. So this was the important work, because it told you how to address this question, how to verify it numerically in a given system, and essentially to highlight it that choose your favorite model that you're interested. If you are, I don't know, condensed matter physicist, and you will find that. Just you should know where to look at, right? So in that sense, that is an important work that highlighted that actually this does apply to most physical systems of our interest. And the language that I will use in this presentation will also follow the language used in this paper. Now here, let me just for the sake of generality, let me comment on few other properties of quantum systems that thermalize that are often also discussed in the literature, and I will not have much time to discuss them. But in principle, when one talks about isolated quantum system described by some Hamiltonian, in principle one has eigenstates of the Hamiltonian, one has eigenenergies of the Hamiltonian, and then finally one has observables and expectation values of observables in Hamiltonian eigenstates. Well, this is like, you can see it as a triangle, and different people in different parts of history focused on different properties of these systems. So for these two parts, there were many interesting results introduced in the literature that I will not have time to go into details. But of course, the fact that system thermalizes is to a certain extent visible already in the structure of Hamiltonian eigenstates as such, without looking at observables. And this is something that this is a direction of research that actually was born even before one really started to look at the matrix elements of observable. Another very important attempt to describe chaotic and eventually thermalizing systems is to study the statistics, the spectral statistics of the spectra, statistical properties of the eigenspectrum. In particular, there was this so-called quantum chaos conjecture in the early 80s, stating that quantum systems whose classical counterparts exhibit chaotic behavior, then in the quantum limit, their statistics agree with random matrix theory predictions. That is called so-called quantum chaos conjecture. Of course, that conjecture relied on, first in the 80s, relied on systems, on physical systems that do have their corresponding semi-classical limit. Now, in the early 90s, it was realized that actually typical condensed matter systems, at that time it was the TJ model that was popular because of the cuprate superconductors. I think in '93 it was the first study of spin 1/2s in the TJ model that doesn't have really the corresponding semi-classical limit, but still the authors showed that these systems exhibit random matrix theory statistics as well. So that was one very important direction, which is still relevant nowadays to study spectral properties. But I will not, here in this respect, I will stop. I will not make any further connections between the spectral statistics and thermalization. Of course, it is assumed for most of the systems, for the overwhelming majority of systems we will study, that actually if they thermalize, they do have random matrix theory statistics. So the main focus of my presentation here is to focus on eigenstate thermalization hypothesis. In particular, I highlight this review by D'Alessio, Caffrey, Rigol, and Polconico that is now 9 years old, and many of the aspects discussed in this review I will also discuss here. Okay, good. Now, plan of the lecture. Now, this first point I already discussed. And there are two other points that now I will focus for the rest of today's lecture and tomorrow. So these are the 2 points. Now, what are these 2 points? So these 2 points are essentially, they look similar, but they have differences. Differences in the sense that first I will just consider general framework. I will ask questions such as, what is eigenstate thermalization hypothesis at all? Why does it imply thermalization? So what are the necessary conditions? Is ETH the only condition? If not, is there something more? And then I will try to argue where does ETH come from, how to derive it, so that physicists are satisfied, not mathematicians. And how to then justify that the Srednicki ansatz is the proper ansatz relevant for physical systems of interest. Then in the third part, then I will focus on physical systems, and I will try to make distinctions between different behaviors of physical systems, and I will try to make distinctions between physical systems that thermalize, physical systems that don't thermalize, and what are the subtleties involved involved in all these systems. Okay, this is now my plan. Now, as I said, I will first, for today, I would like to go through both points without going into too many details, so that you see the scope of the lecture. And then I will come back, actually tomorrow I will come back and I will then try to sketch you some proofs or some derivations of some properties that are interesting enough for you to, so that you will once see how the things are understood or argue that they should be valid. Okay, so any comments or questions at this point? Yes.
What does typical mean?
So the way I can give you like a physicist answer to that. Typical mean that in principle things. Typical means that all but something that is measured zero. So we can say typical physical Hamiltonians, they exhibit a system governed by typical physical Hamiltonians, they will thermalize. Apart from Hamiltonians that are measure zero. Now in this measure zero Hamiltonians, of all possible Hamiltonians in the world, there are some of them that are very important, such as integrable Hamiltonians, XXZ, Heisenberg integrable chain, and so on, right? There's unproportionally many physicists interested in integrable systems or special systems relative to all other Hamiltonians possible in the world. But of course, there's a reason, because they have first beautiful mathematical properties. They have special mathematical properties. And in terms of applications, they may be useful. They may be different. They may show, I don't know, storing of quantum information or something that can be used in some applications. And that is why we are all interested in that. But if we consider typical, we consider like measure zero of all such examples in nature. Yes.
What do you mean by integrable?
Yeah, thank you for, yeah, okay, yeah, thank you for this question. So, yeah, sorry, I should have clarified that earlier. So, I'm talking about quantum systems in isolated from environment. So, if a given quantum system is isolated from environment, that means that the energy of this system is conserved, right? The energy is a conserved quantity. Now, in most physical systems of interest, things like particle number is also typically conserved, because if we don't exchange anything with the environment, then we also don't exchange particle. If we deal with Hamiltonians that describe, I don't know, fermions or bosons or so on, right? But these conserved quantities like total energy or particle number are just few. Let's say order 1, 2, 3, and so on, right? Now, you can ask, are these the only conserved quantities in the system for most, or let's say typical Hamiltonians? That is, the answer is yes. But you can find physical systems like the most famous example is one-dimensional Heisenberg chain, transition invariant Heisenberg chain, that has more conserved quantities. More conserved quantities than just energy and particle number, or the total spin SZ magnetization. Now, it's not only that it has more conserved quantity, it has extensively many conserved quantities. So when you increase your system size you go from L to 2L, then it means that the number of conserved quantities has also increased. On top of that, these conserved quantities are such that they are relevant for the physical observables that you're interested in. Physical observables that you're interested in, they are typically local in some space. And if you have additional conserved quantities that are important for these observables, have, mathematically speaking, some overlap with this observable, then they will be important. You have to take them into account in the description of dynamics. And as a consequence of this conservation law, it may appear that your expectation value of observable will not match the predictions of statistical ensemble. You can, of course, argue that all systems, all isolated quantum systems have many conserved quantities, which are projections, which are called projections on eigenstates. These are, of course, to a certain degree, these are mathematically speaking conserved quantities, but they are non-local conserved quantities and are not important for the outcome of the experiment that measures local observables. Yes.
How much you said there is a clear relation from integrability and thermalization.
Yes.
Can I see why it appears? So how is an integrable system will thermalize?
So the general wisdom is that integrable systems do not thermalize. Do not. So the example that I have shown you here, so if you want the typical example, typically experimentally relevant example, is this, right? So this is, mathematically speaking, this is to good approximation, this is one-dimensional Lieb-Liniger model that is known to be integrable. Because it's integrable, it has conserved quantities, and these conserved quantities impact the dynamics of observables. Now here I have to be actually careful, and that is that is also the purpose of this lecture, just to correctly answer these questions. Okay, so I have to be here precise. So here we say, well, you see, quantum many-body systems may not always thermalize, and the reason is integrability. Now, that's fine. That's a correct statement. Now, the subtlety in this statement is that Dave Weiss and collaborators had to do something very clever and very brutal to this system to observe that. Most experiments that they could do, or most quenches, quantum quenches that they did, would not show anything interesting. Okay? So the point is that they had to do such kick. They had to prepare such initial state that for given observables they can measure, and I guess this probably comes from time of flight measurements, that given observables they can measure are good observables to detect features of integrability, and the initial state is such that the distribution of conserved quantities that exist in this model are so atypical that they impact given observable that they measure. Okay, so it was non-trivial to find such example, because most of the things they could do, they would not see something featureless, even for integrable systems.
So we are interested in out of equilibrium dynamics.
Yes. Yes, this is why I started with the ice cream. Yeah, that is the point. Yeah, so ice cream is far from equilibrium with respect to summer, let's say. Yes. 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 So yeah, thank you for this question. So let me repeat the scope of the lecture. So I'm interested in let's say circumstances that are as brutal as possible. So we are considering system that has no influence of the environment, and we perturb it or we quench it as much as we can. And we ask, is it still possible or does it still happen that such an isolated quantum many-body system in the thermodynamic limit, so when the number of degrees of freedom goes to infinity, still exhibits after sufficiently long time a behavior in which time-dependent expectation values of observables match with statistical ensemble predictions?
I have a question.
Yes.
This case, is it understood on what time scales it's going to actually thermalize?
Yes, yes. That's, of course, a good question. I think it's understood theoretically. Experimentally, I guess it's hard to distinguish. Well, experimentally, it's a harder question because you have to then distinguish between different sources of integrability breaking. You have to then determine what is the main source. So, of course, the answer is non-generic, and I guess, so there are many possible answers, and this is, of course, a very, very active research direction. So the most common wisdom that you can apply is that you say, well, there is some perturbation that breaks integrability, so there is a time scale that you can estimate from Fermi golden rule. Okay, so that you consider essentially matrix elements of the perturbation in the integrable system. You get some rate, and the inverse of this rate is essentially, you can call it thermalization time. And of course, this is then inverse of the coupling, right? And so if the coupling is small, then this Fermi golden rule time is 1 over small coupling squared. And this can be very long. much longer than the time scale of the experiment. But other scenarios may also exist. Right. So what I want to say, time scale for thermalization here can be in some, so Fermi-Golden rule type is such a Fermi-Golden rule type of argument for thermalization is polynomial in small parameter, but it can be even more brutal. It can be exponential in small parameter, and then it can be, this pre-thermal regime can be even longer, so that you will actually, can be even as long as the age of the universe. So then it's hard to distinguish what is really per-thermal and what is really a new phase of matter.
There could exist some observables for which it will be dependent on the system size in a way that will go to zero quickly.
You mean the relaxation time that is depends on system size, or the?
Yeah, I just find it interesting that this doesn't depend on the system size, so that it stays finite in the large system.
Well, yes, that's again, that is also a good question. So you have many observables, and observables can have different relaxation times. That's always the case. Typically in theoretical analysis, we would like to study observables that have the longest relaxation time, because if we study the breakdown of thermalization or the onset of thermalization, we want to be as rigorous as possible or as brutal as possible, so we measure the one that has the longest relaxation time. Now, of course, there always exist observables, even here in the case, that have relaxation time that is of the order of order one in terms of model parameters, that will immediately approach the thermal predictions. But then they're not as interesting as the other ones. Yeah. Okay. So by the way, my time says it's almost 45 minutes. Is that correct? Possible. Now we can actually make a, I don't know, 10-minute break or so, because, well, I wanted now to start on the
Let's ask.
whiteboard. Is it okay to make 10-minute break and then we continue? Well, as I understood, we are flexible, right? We have 2 hour. We have 2 hour. So yeah. So let's make maybe 10-minute break and then we continue, so that we don't use the computer anymore. Okay. Thank you. Yes.
I have a simple question.
Yes, of course.
Regarding integrability, because in the NBR case, we had this famous Albert Hamilton. The
Yes.
question is if all integrable Hamiltonians will require that diagonal, let's say, diagonal construction in terms of the constant of motions.
Oh, it's like non-integrable of the same. You can write any Hamiltonian in T-base.
No, but I mean, my question is in terms of these integrals of motion.
A quantum system, you have all these extensive integrals of motion. Let's mention that projectors to the Eigenstate.
Right. Okay.
Another example, just powers of the Hamiltonian. They can use with the Hamiltonian, and because van der Waals, the independent.
I have a complaint, which you probably want to correct, or the integrability definition.
Yes.
So what you say is like
Two. Thermalization and ETH. General considerations. Okay, so let me start with the first question that actually I kind of touched upon before, but let me be more specific in that respect. So the first question is about definition of thermalization. Definition of thermalization from physicist perspective. Okay, the first thing is which observables we look at. And in principle, my answer is clear. These are few body observables. So this is something that it's always a discussion, right? Is it, people say, local, non-local, few body, multi-body. There are always these buzzwords around. Now here I say in principle few body. Now that does not exclude also sums of few body observables, but what I have in mind here are observables that can be such as site occupations, quasi-momentum occupation, or similar, kinetic hopping, and so on. Now here I highlight one thing, that I don't require locality in real space. So for example, you can consider quasi-momentum occupation, which is a totally legitimate experimental quantity you can measure via time of flight. As you know, quasi-momentum occupation, if you write it down in real space, it's a non-local observable because it has, I don't know, a dagger A with two different indices on the lattice that are non-local. Okay, so for me, I still consider it as a valid observable.
Can we say that all these observables are in any case K local?
Yeah, in some sense. So quasi-momentum occupation, you can of course go to quasi-momentum space in which this observable is local.
Yeah.
Right. So if I try to generalize it that way, if there exists a physically relevant space and quasi-momentum space is physically relevant, then locality in that space is enough. Okay. Now, of course, I need to be honest here with you. That's why I'm here, right? So because you're young and you have to understand all these possible, Now, when I say, well, quasi-momentum space is a valid space for me, yes, because there are time-of-flight experiments, you can measure that in a given, I don't know, ultra-cold atom experiment. Now, some people like transport a lot, and they may now object and say, well, how do you measure transport in quasi-momentum space, right? Of course, in that sense, quasi-momentum space is not a valid space, because if you're interested in current, which is something typically measured in condensed matter, you have voltage on two edges, right? That's very special conditions, and only real space is then the proper space, right? There is no voltage, well, at least I'm not aware of routine experiments that do voltage in quasi-momentum space. Okay? So we have to take everything with a grain of salt, but for the level of this analysis, I will have in mind real space or quasi-momentum space as equally good spaces. Right? So now, if I want to draw a typical picture of a setup that I'm interested in, you can consider, let's say, a chain that has spin 1/2 systems. So qubits, interacting qubits, that's a typical example we're interested. So these are sides of the lattice. J goes from 1 to L. Let's say L is the number of qubits that I have in the system, so spin 1/2. So let's say at some side J, I have the operator SJC, right? This is a typical observable you can study. So like a magnetization, projection of magnetization in the Z direction at side J, that is a typical few body observable. Now, as I said, I'm not, that said, I'm not excluding now observables which are sums of few body observables. So these are observables of the form, let's say, sum over J, OJ, where this OJ is something, it's a few body observable that has support on an order 1 number of sites centered around site J. So I'm not excluding such observables, but I need to highlight one thing that is maybe now a bit subtle, but I will still highlight it here. I will come back to this issue, I guess, tomorrow. I will not have time today to address that. But there's another important thing about ETH, which you can consider as a technical aspect, but at the end of the day, in some cases, it's not then so technical. It's actually very crucial. And this is that the observables you consider also, for which you test ETH, whether it's valid or not, need to have a proper normalization. What is a normalization? Normalization essentially is a sum rule over, and I will define it later, okay, normalization. So I will not go into detail so that I will not blur the main picture. But ETH is valid for observables that are properly normalized. So if you allow me for one technical statement now, if you define normalization in terms of scaled Hilbert-Smith norm or so-called Frobenius norm, this needs to be 1. This is like a sum rule of all matrix elements. And if you don't satisfy a sum rule, then of course you can cook up whatever scaling you wish in the ETH ansatz. Okay, so ETH, everything I will talk about is valid for normalized observables. That is the only lesson you have to take at this point here. Okay, that is point A. Now, okay, so which when we talk about normalization, what do we have in mind? We have in mind few body observables. That is the first statement. The second statement is, and that is now a necessary condition for thermalization, is equilibration. So what do I have in mind with equilibration? Let me again be general, just draw a sketch, not to go into any details. So let's say I have my O of t. So that is expectation value of observable in a given pure state. I start somewhere. There is a time evolution. And then after a long time, I reach a stationary state, right? So when I have in mind, when I talk about equilibration, I ask what are the fluctuations, temporal fluctuations above the long time steady state. I call this sigma t, right? So temporal fluctuations above the steady state. Essentially, you calculate the variance of these fluctuations in a given time window, right? So the requirement is that then in the limit when L goes to infinity, right? So this is for a given L. L is the number of qubits in this system. So the limit L goes to infinity, sigma t of L should go to 0. So in other words, I'm excluding here scenarios of thermalization that actually you never equilibrate, but the time average is the correct time average given by the statistical ensemble.
So,
Yes. Yes.
you're taking L to infinity.
Yes.
So for finite L, you do not expect that it will be 0.
Yes, exactly. That's a good point. Yeah, thank you for highlighting that. Yes, any finite L, it's in principle non-zero. It's actually very exotic if it's exactly 0. I don't know such examples. And this actually connects to my story when I was a student. It happened, well, maybe, I don't know, you're always biased in which community you are, but some people approach me like, 30 years older than me, and they say, yeah, you're studying thermalization, but it will never thermalize, right? It will always fluctuate, right? Which is, of course, that is a statement, yeah. So because it's isolated, it has a finite number of degrees of freedom, it always fluctuates. But of course, when you take the limit, that should go to 0. Yeah, sorry.
The observables, just few body observables. So non-local observables will thermalize also? Or?
Well, again, the question is what does it mean non-local, right? Non-local, it means with respect to your preferred space.
If you have not a summation, but for of this instead of a sum of evaluators, a product of this measure, for example, the whole chain instead of just one side, this will
Yeah, so I think this is a question of scaling. So you can have products, but if the support of this products, on the sites on which product is defined, with respect to L, still vanishes in the thermodynamic limit, I would still call it few body. It's a bit semantics, right, here, because you can say, well, what if support grows at square root of L? Then it's not really few body, right? It's growing, but slower than the system size. Of course, such cases I'm not really addressing, to be honest, right? I want to be here strict, so I want to say the support is finite. You can say support is 10, which is fine in principle. If your number of degrees of qubits is 1,000, you don't care about this 10. 10 is like 1.
The sums must be finite. Extensive summations are already non-local in this
So,
sense.
you can define sums of few body, right? Which is extensive sum. So of course, here maybe I mean I need to be more careful. This, let's say, goes from 1 to L, right? Right? So this is extensive and this is still, right? But the only point is that then you have to care about normalization.
And I guess when you talk about equilibration, you need to be careful about which of the limits you can.
Exactly. I wanted to highlight, I'm coming there. Okay, and then now, as you can imagine, then it's point C. So this is then the point C is agreement. Agreement. Is it correct? Agreement with statistical ensemble prediction. In the sense that my O of t, expectation value, time average, equals the O in the statistical ensemble. Of course, here I have in mind Gibbs ensemble or well, canonical, grand canonical, or microcanonical. I will not make sharp distinctions between this ensemble. I will write SE as statistical ensemble prediction. Okay, this is the time average. Now, you can, of course, ask now about details as Dario asked. So choice of observables is the most crucial thing because that's something that is here defining properties. But then there are other questions. Let's put it like this. Or let's say questions or concerns that are also important. Now, one thing is the relevance of initial states. Then another issue is the time interval of interest. And the final one is the sequence of limit.
So about point B.
Yes.
Do we have any requirements how fast it should go?
Yeah, that is a question. Now, a general answer is no requirements, right? It should happen at some time. Now, of course, that also depends on the choice of the initial states that you are studying. Now, typically, or in most cases, the initial states that you study have some sort of spatial, of translational invariance, right? They're in some sort homogeneous. Now, you can also study initial states that are inhomogeneous, like, and that's a typical example, it's a domain wall. If you consider a domain wall, which is of, let's say, two semi-infinite chains, so you couple a chain that is like polarized, half of the chain is polarized up, half of the chain is polarized down. Now, what is the time scale for the system to reach a homogeneous state. Of course, that should scale with the system size, because if your system size is twice larger, then it will take more time to relax. In this sense, relaxation, the time for equilibration and thermalization will diverge with L, right? May go to infinity, but I don't think that's a problem. That's according to this definition. Now, you can always ask how long should you wait so that you can still say that you have thermalized. So how long is long enough, or how much time do you have to wait? Right. So I can give you like a more theoretical answer, and I can give you more practical answer, right? So theoretical answer here that I think it's a proper answer I think it's a consistent answer to set the framework, is that you have to wait until the longest time available of the system, and this is essentially inverse of the level spacing of the many-body spectrum. Right? So we are dealing with quantum systems. Quantum system has a quantum many-body system, has a given spectrum. That spectrum is discrete because it's finite, has a level spacing. Level spacing is very small because if we are dealing with L degrees of freedom, so the Hilbert space dimension of such system, let's say without any other constraints, is 2 to the L, right? Exponentially large in L. Now, a typical level spacing in your quantum system is 2 to minus L. Right? This is, sometimes we call it, because of this discreteness, we call it Heisenberg energy. And then inverse of the Heisenberg energy is then Heisenberg time, 2 to the L. And so definitely, if you're thermalizing, you have to do it before the Heisenberg time. This is a conservative answer to that. Now, you know in practice that it's maybe even good to thermalize even before that, right? This is like answer, if you ask me a question, if you want to graduate and you're a good student, but you don't pass exams, right? And then you say, okay, well, I have 4 years, I have 5 years, I have 7 years, well, I have 10 years and so on, right? In principle, if somebody pays your tuition and so on, you can study forever, right? But our lifetime is still finite, right? So it's good if you really want to graduate, you should do it rather fast, right? Don't wait too long time. That is now more practical answer to this question. So in ideal world, if we are dealing with initial states that are not inhomogeneous in the sense of domain walls, then we would like to see that actually this thermalization happens on times that don't scale with system size. Okay, but in some cases you have to, So look, thank you for highlighting that. In principle, when you talk about thermalization times, they can scale polynomially with L, or they can scale exponentially with L. This is what I highlighted here. So that's the Heisenberg time, which is let's say the longest, the upper bound scales exponentially with L. And you can think about the true time scales if you convert it to physical units. In many cases, you will see time is like h of the universe, right? So exponentially in L times are typically very long. Now, what even highlighted is that if you have to wait just polynomially in L long times, then that's fine. Right? That typically we are happy with that. So if you have a typical system that exhibits diffusion, then the diffusive time, or the time, typically we call that tauless time, the time that you need from to propagate, for an excitation to propagate from one edge to the other edge, scales with L squared. And this is time that is still slow enough so that we say if we thermalize after that time, that's okay.
It's important also how the interactions happens between the particles, right?
Yes. What I have in mind here, if I talk of initial states that is like a domain wall, then I have in mind system that has short-range interactions. If it has long-range interactions, then, well, okay, you can still study domain walls, but it's probably less interesting, because if you have all-to-all or let's say longer range, then yes, exactly. Yes.
You said the observables we were looking at still have this oscillating behavior, but the average goes to what we expected in the ensemble, right? So, but we still have to need some like maximum oscillation possible, because if it's oscillating too much, depending on when you measured, you could be too far away from the
But this is point P, I think.
Yeah, yeah.
Is there another definition that must go to zero, right?
Well, yes. So, but yes, but that's actually more subtle point even because in principle what I was talking about, if you now study the distribution of these values, it's somehow like something like this, right? And what I'm saying is that the width of this distribution shrink to zero. But if I guess correctly, you're highlighting that there can be some events far away from the mean, right? And you can be unlucky and measure your observable at a given time where you measure this value, right? And this may appear as non-thermal. Of course, such events may exist, but then, you know, you can read, if I want to be more formal or more mathematical, then I have to make statements as such as for most measurements or for most typical times and so on, that will happen, right? Yes. It should, yeah, yes. Now, this is the question after, how does this time scale, right? Whether now this is again exponential in L or shorter, right? So yeah, so what Ivan said, of course, if you went for long enough, it may happen here that, you know, we have again something like this, right? Which you cannot exclude, but again, for the typical measurement, for the overwhelming majority of times, it should be close enough to the average value. Okay. Good. Okay. That was like okay. That was the well, I just now talked about definition of thermalization. Now I will erase that. I will erase this and then come to the second point. Okay. The second point is, well, what do we actually have in mind with ETH? So ETH, that was already part of the first, that was already mentioned in the first part, is of course, when you talk about ETH, we have in mind a statistical ansatz for the matrix elements of observables in Hamiltonian eigenstates. So let's assume that you have Hamiltonian, for which eigenbasis I denote as ket alpha. Eigenenergies are E alpha in an eigenstate alpha. So then the statement is that the matrix elements of this of observables, of our observables in Hamiltonian eigenstates have the following structure. There is a smooth function that describes the diagonal part, and then there is the fluctuating part. The fluctuating part goes as, if there is another smooth function f of E bar omega r alpha beta, that's the random stochastic term, and then there is a suppression which I describe as rho of E bar to 1/2. This is the, with rho, I have in mind rho of E bar is the density of states, many body density of states. So if you ask how this is really defined in a given system, in a finite system, it's essentially delta n over delta E, right? Okay, probably properly normalized because that should be in dimensionless units, but the point is that you have to calculate in a given narrow interval, you have to calculate how many states there are. Now, in many cases, I mean, that was introduced by Mark. Actually, this term was expressed as E to S of E bar, where S is the microcanonical entropy, essentially log of the density of states. Now, I have to define what is E bar. E bar is the mean energy, E alpha plus E beta half. And then I have to define what is omega. Omega is E alpha minus E beta, is the difference of the energy. Okay, R alpha beta is the stochastic term, so something that when you measure the average of that is 0, and the variance, let's say, is 1, or it's normalized. It's something that should not scale with system size, because what scales with the system size is this. Now, this is the so-called ETH ansatz for the matrix elements of observables introduced by Mark Srednicki. And now let me now I hope that most of you already have seen something like this. Now let me comment on the meaning of or let's say the origin of these terms. How to understand that? So actually, this term has two contributions. Okay, let me use colors. I will use the blue color. It has two contributions. This contribution and this contribution come from the random matrix theory. So these two contributions is something I can essentially, within the random matrix theory, I can derive them. And if time permits, I will do that tomorrow. Then, on top of that, you have this. You have these two smooth functions. Oh. On top of that, you have this thing and this thing, the two smooth functions. That is something, that is a non-trivial contribution by Mark Srednicki, and this incorporates physics. In physics, in the sense that different observables, different Hamiltonians have different smooth functions. So if you ask now, what is the non-trivial part of the ETH ansatz, or what is the beauty of the ETH ansatz? The beauty is that this, let's say, quite straightforward or quite mathematical ingredient of random matrix theory is married with real world, physical world, expressed via these two smooth functions, O of E bar and F of E bar omega. So at that time, when Mark introduced that, of course, that was non-trivial, because he didn't, if I understood correctly, at that time, he didn't have any numerical tests to check that. That was like a conjecture, which indeed turned out to be, for most physical interests of interest, a very good description of what we really observe. Okay, so this is what I call Srednicki ansatz. As I said, Srednicki ansatz or ETH ansatz is something that has, at this point, for this level, has the same meaning. Now, let me now highlight the thing that I already said. What is actually the RMT contribution? So maybe before I specify that, I should make the following statement. I should say that if you ask, can we prove ETH mathematically rigorously, That's a hard job just because of these smooth functions, because they are specific, right? They depend on your system, on your observable, on your Hamiltonian, and so on.
Or can describe.
And so a given system, different observables have different smooth functions.
Yeah, I can have the same system with different smooth functions, like
different observables.
Okay.
Sorry, for different observables. I mean, yeah.
Yes. Now, yes.
I never, I always get, I never remember. I mean, this is in a physical system, this is true for eigenstates that are sufficiently close in energy, right? While instead for random matrix theory would be, let's say the ansatz would be satisfied for any pair of eigenstates. Am I right?
Well, here in principle, yeah, yes, you're right. Now, if you ask, well, you can ask how different in energy this eigenstate can be so that this is valid. Now, here, the nice property, which is, of course, not included formally on this level, is that actually this smooth function f of E omega has a pretty sharp decay at large omega. So if omega is too large, in any case, matrix elements are brutally suppressed. And this actually suppression goes for omega, which is order 1, right? As we know, energies are extensive in principle in a short-range system, right? Scale with L. But even if you take a macrocanonical window that has a finite energy interval, which means that it vanishes in the thermodynamic limit, the energy density vanishes, right? It's still sharply suppressed. Okay, now ETH okay, let me make now two statements just for completeness, right? It is sufficient to explain quantum thermalization. So its existence, its validity is sufficient to explain quantum thermalization. Now here I have to, again, be honest with you, put such a star, okay, because there are two other mild assumptions that I have made on top of validity of ETH. And we'll see them later, probably tomorrow. And I can already tell you what are these two mild assumptions. First mild assumption is that we consider system with energy spectrum that is non-degenerate, so absence of degeneracies in the spectrum. And the second assumption is that initial state is such that for a given quench that we consider, the projection on initial state in the eigenbasis of the Hamiltonian is such that essentially the width of this initial state shrinks to 0 in the thermodynamic limit. So if we have some very weird initial states that couple non-trivially to eigenstates at different energy densities, right, then that may also cause breakdown of thermalization, but that is unlikely for most experimental situations we have in mind. Okay, and both conditions will enter at some point, probably tomorrow, and I will again highlight that where it enters.
So for instance, if I start from this state with all the spin up, I would guess that typically we'll have, let's say, an expansion on all the eigenstates of the, because if the Hamiltonian is very random, I would say that.
Yeah. So let's say that this is the eigenspectrum.
Right.
If we have initial state, let's say I consider projection on initial state on the Hamiltonian eigenstates, alpha, right? Typically, then we have something like this, right? So now the statement is that in terms of energy density, right? Because the energy density corresponds to a given temperature, then this width, let's call it sigma E, right? Should go to 0. In terms of energy density. Of course, the width of the initial state in the unscaled units is in principle square root of L, goes with square root of L, but if you divide by L, that should then shrink to 0. Yeah.
Let me just ask, this rho of E bar is, am I right in thinking it's a density of states as a function of energy E evaluated at the mean energy E bar?
Yes, yes, yeah.
So what is the normalization you're implicitly assuming here on rho of E itself?
Well, yeah, the normalization is such that the integral rho of E dE, the integral is then the Hilbert space dimension.
So
Yes.
that 1 over rho E bar to the half is roughly speaking a 1 over the square root.
Yes, exactly. Yes, exactly. It's a good point. Yeah, I should have highlighted that because that's important for the understanding. Yeah, so I should have highlighted that before. Sorry for that. I mean, well, it's related to second point that I wanted to make. I mean, right. So just to highlight, it's a trivial point, but let me highlight that. So ETH is a hypothesis. Okay, so there's no rigorous mathematical proof, as that's the H in the abbreviation, ETH, right? Now, you can now ask me, well, how can it be? It's, you know, there's some hypothesis, but now you're talking about that you're giving lecture and then so many people study that and it's so well established and so on. Well, it is very well established for overwhelming majority of physical systems because it's very easy with nowadays computational facilities to check whether EDH is valid or not. And you can check that because of this brutal suppression that goes with the Hilbert space dimension, which is exponentially large in L. So if you study matrix elements using nowadays computational resources, it's very easy to see exponential decay of something. Usually, so even if you do exact generalization, right? So if you want to have eigenstates, you want to have observable matrix elements, you have to get eigenstates of the Hamiltonian. As you know, or you may not know, but I can tell you, it's computationally costly to diagonalize full Hamiltonian of an interacting system, right? And then you can see, because that is costly, you can do, I don't know, for spin chains, you can do, I don't know, 16 spins or 18 spins or 20 spins, or if you have some super good techniques, you can do 22 or you can do even 24, but it's still very small. So you can see you can hear very often in some community or from some people saying, well, these are in any case small size calculations. So who cares about small size calculations? Well, that depends on the problem you're studying, okay? If you want to study that, actually, exact generalization is pretty good method. So if ETH is valid, because of this term, right, which scales exponentially, so rho of E is proportional to 2 to the L, if you consider now typical qubit chain, right? You can see that very well by studying finite system sizes, 12, 14, 16, 18, 20. It's very obvious. So because of that, even though it's a hypothesis, but for most physical systems, we have no doubt that actually this is really valid. Okay. Yeah. Now, point C is something that I also have mentioned, and this is that ETH can be reduced to its primitive version, right? Or let's put it like this, simpler version. Is the so-called random matrix theory ansatz. So instead of ETH ansatz or Srednicki ansatz, I can cook up RMT ansatz. RMT is random matrix theory ansatz. It's essentially the same thing, but here with a simplification. O of E bar is 0. F of E bar omega is essentially 1. No omega dependence. Okay, and this is the thing. So when one considers the RMT ansatz, essentially, you can prove that. Again, for the satisfaction of physicists. And I will do that tomorrow. Okay? Okay, so let me put here summary of section 2. So everything I have discussed so far on the whiteboard is that ETH, so Sredniki ansatz, implies quantum thermalization. Okay. Okay, I need to erase now this, so if you have any other questions, now we can address them.
I think that ETH is very important to justify, or not justify, to describe quantum thermalization, but I see that it doesn't just describe it, right? It's more general. Like when you have the vanishing term, right? It's more general than when you take L to infinity, I guess, or not. So what I mean, we are always in the thermodynamical limit of infinite size system, or for ETH, it doesn't care about it.
Yeah, so thank you for this question. Yeah, that's of course the main question here. So in principle, the answers that I defined makes only sense in the infinite systems, right? So in infinite systems, L to infinity, there's no this fluctuating part. Fluctuation do not exist. What does this mean? This means that essentially eigenstates that are sufficiently close in energy, they're indistinguishable. What does this mean in physical context? It means that essentially, if you prepare your initial state at a given energy, you can prepare many different initial states at a given energy, but essentially they all give you the same outcome of the non-equilibrium experiments, which means that the memory of the initial state is lost. And this is the feature of thermalization. So if you forget about all these details, it's just that you have independence of the initial state, which is the key ingredient of thermalization. So ETH in that sense incorporates that, but it's more because it tells you in finite systems, it tells you how this is, how all these issues about, I don't know, fluctuations in time and small deviations in finite systems, how this is reconciled. Yeah.
Thank you.
Okay, yeah. Yeah, good question. So
The ETH answer is spectral function.
yes.
So it is an answer can classically compute as well.
Yes.
So how does it connect?
Yeah. Yeah, how does it connect? So in principle, the way how this is here stated doesn't care about this classical limit. So the way how this is derived, it really comes from the stochasticity, or let's say random matrix theory behavior encoded in a given system. And then what is described in the ansatz is simply fluctuations that emerge in such finite systems. Now, of course, this f function, as you have highlighted, is related to the Fourier transform of the autocorrelation function. That's a quantity you can measure in any physical systems, no matter whether it's classical or quantum. And of course, this f function carries some information what type of dynamics you have. And these dynamics can be different, can be diffusive, or can be something else, and can be very similar in classical or quantum systems. Now, the ETH has a given, so the power of ETH, that's kind of related to the previous question, is that it really quantifies how the fluctuations behave in given finite system. Now, how to translate that in the classical language, I cannot give you the proper the full answer at this point, but you can imagine that in any system you can calculate time evolution, you can calculate the temporal fluctuations, that you see of, let's say, autocorrelation functions or similar quantities, and then you can study, you can understand that in terms of probably some other theories as well. Yeah.
Is this frequency on the ETH answer related in the time evolution of the operators?
Yes, yes, we'll come back to that. I mean, we'll come in the second part of the lecture, so likely tomorrow, we'll explicitly consider time evolution, and then we'll see the consequences if ETH applies, how does time evolution correspond to the agreement with statistical ensemble predictions. Okay, now, yes.
We are assuming we are somehow perturbing our system for a given time, right? But did we make some considerations about these perturbations? Like if it's a perturbation, I think it's small in relation to something. Like
so
to what?
Essentially, the only requirement is that the initial state that is then subject to time evolution is not an eigenstate of the Hamiltonian. Actually, it's far away from eigenstate of Hamiltonian. So what do I have in mind when I say that? So the perturbation in principle is strong or arbitrary, so as strong as you wish. So what do I have in mind with that? I have in mind that the projection of the initial state on the eigenstates of the Hamiltonian is something that is non-trivial, in the sense that you're not starting with the initial state that has just projection on two eigenstates of the Hamiltonian. This is something you can hear when, if some people want to challenge you. They say, well, how about I design an experiment where my initial state just couples to two Hamiltonian eigenstates. Then I will oscillate forever, and then there will be no equilibration. Of course, theoretically, that's possible, but experimentally, I guess whatever you do, in the language that I used, you couple or you project your initial state on extensively or on exponentially many Hamiltonian eigenstates. In other words, the entropy you're producing is extensive, right? This is like log of the effective Hilbert space onto which you couple, and that should be exponentially large. So log of exponentially large is proportional to L, so it's extensive. So typically you do quench and you're generating extensive amount of entropy. This is the physical situations present in the experiments. And this is something I'm addressing here. Okay. Yeah, so I have 10 more minutes. So let me now go to the third point, which also I find important. Just to be aware of the content now, where this is applied or where is this not applied. So, okay, I put in the slides, I put the title ETH and thermalization in physical systems, but let me be here more specific. Let me write emergence of thermalization. Emergence of thermalization. And validity of ETH in physical systems. Now, why did I write it that way? You can already guess that if I write it that way, I want to highlight that that's not exactly always the same thing. Okay? Now here I go. Now, the previous section was more general, right? Simpler, right? I introduced ETH answer. I say, well, if that is valid, you have thermalization and so on. It's a happy life and, everything is clear and let's go home. Now here I want to highlight that now emergence of thermalization and validity of ETH, when it goes to real physical systems, there can be subtleties. Some differences, some things in common, some things different. This is what I want to highlight now in this section. So what is the plan here? What do we want to consider? Let's make some imaginary axis. Okay, so this is like a complexity of physical systems. Now, here I have to be honest and I have to make a disclaimer before I do anything, right? This complexity, every senior physicist can write their favorite diagram of complexity. So that's just one possible just one possible illustration. So I will put here, I will consider three categories. One category is few body systems, right? Systems of just few degrees of freedom. Then I will put here many body, non-interacting. Right, so I will consider system that has extensively many particles or degrees of freedom, but they are non-interacting. And then finally, I will consider many body interacting. Okay, now, well, I also need to, yeah, with time, it's always, takes you always longer than expected. So how much time I have? Around 10 minutes or 5 minutes? Yeah. So, okay, I mean, just not to be too simple, I will not comment much about few body systems. I would just say with words, okay, so that I don't lose too much time. Of course, few body systems, you can consider qubit, 1 qubit, 2 qubits, and so on. You can have Hamiltonians. Now, as you can imagine, that doesn't really fit to my framework because I don't have this L, the number of qubits that goes to into the thermodynamic limit. So in principle, I cannot define ETH there, right? Because there's no scaling, regime there. Now, still it can happen, and well, now if that was like 1 week lecture, I would then use one day just to have an example. I can cook up a qubit system and I can do some quench, and I can show you that I can easily find observables and initial states for which time average of a given observable equals exactly the same as statistical ensemble prediction. Okay, so that is just to say that even in finite systems that don't have the proper thermodynamic limit, you can always find observables, you can always find quenches after which time average of a given observable matches statistical ensemble prediction. Does it mean that the system has thermalized? No, because at least to this framework that I'm here advocating, when I talk about thermalization, I have in mind essentially independence of observable you choose, of course, provided you stick to few body observables, and essentially independence of initial states. Right. So always, even for cases when you say, well, I found the breakdown of thermalization, even in most brutal cases that violate ETH, you don't thermalize, you can typically always find observables, quenches, where everything looks perfectly thermal. Okay, that is just for you. Maybe it's a trivial statement. I want to highlight that because just to avoid wrong impression. In principle, the statement of thermalization is a rigorous statement in the sense that if you find out of 100 observables or 100 initial states, if you find 99 cases that confirm your expectation that something thermalizes and you find one counterexample, then it doesn't thermalize. In principle. Now, you can use then different language. You can say, well, this is strong thermalization, or you can use different notions, right? Here, I would just simply say thermalization. Okay. This is what I want to say about few body. Now, many body non-interacting, it's a bit more, it's already a topic I can spend more time on that, but I will now finish here, but let me just highlight the main feature. So in many body non-interacting systems, one can show that ETH is violated in a sense that there exists so-called maximal outliers. So what are maximal outliers? Maximal outliers are such that limit L goes to infinity, O alpha alpha minus O, let's say, microcanonical average at the same energy is not zero. Okay, so if I'm more pictorial, if I calculate O alpha alpha, which is just the matrix element in an eigenstate alpha, as a function of E alpha, let's say these are the matrix elements, there are some matrix elements, right, whose this difference does not go to zero. This is what I call maximal outlier. Sorry? What the upper?
Yeah, can you say it's less than some number?
Yes. If the observable is properly normalized, if there is a sum rule, then I guess then you can bound it. Yeah. The same. I'm just not now talking about interacting integrable, not to complicate my life, but it's the same. Yeah. So okay, I'm now finishing with complementary thought. That's now the last thought of this lecture, which is well, I hope it will not be too complicated. I will try to be as clear as possible, but you should judge. Okay. So now, what I'm saying, that's a subtle statement now. So here, this statement that I made is general, and one can actually prove that. I mean, at least I had a paper two years ago where we proved that. I'm not giving my hand on fire. We were the first in the world to do that. At least to my knowledge, we were the first, but it doesn't matter. It's not important. That's a general statement you can prove. Because of the non-interacting nature, such outliers exist. In this sense, ETH is violated. Now, I have to be here careful because I'm dealing with non-interacting system, and I want to say that ETH is valid in many body eigenstates. Many body eigenstates, so far, I haven't really made a distinction between many body and single particle because I said I'm interested in qubit systems, L qubits, which is naturally means I'm dealing with single particle states. I'm dealing with many body states, right? Because I'm dealing with interacting system. Now, if I'm dealing with non-interacting system, many body state, as you perhaps know, can be expressed as a product of single particle states, right? So this statement refers to ETH in many body states. Okay. Now you can define ETH ETH can be also defined or studied. Well, not defined. I think it's more fair to say studied in single particle eigenstates. Right? So let's say that. So why is this relevant? This is relevant because I'm dealing with non-interacting systems. Right? So let's say H in, let's say, N is epsilon L, epsilon N. N, so these are single particle eigenstates. Then I can define ETH, just analogous, in analogous form, delta N M, plus 1 over rho single particle to 1/2 f of epsilon bar omega r and m, which we call single particle ETH. Now here the crucial point is that this is single particle now density of states. So typically scales with L, not with 2 to the L. If I'm considering 1D system. Now if I consider D-dimensional system, then it's L to D, right? D is the lattice dimension. So if I'm in 3D, it's L cube and so on. And now
this is also easy to test numerically because
yeah,
in
yes,
that case
yes.
is this
Exactly.
Yeah.
It's the same difficulty.
Yeah.
Yes.
Okay.
Yes.
So can I ask what it means
Yeah.
conceptually? To talk about ETH, single particle dense.
Yes.
In the sense that I do understand that you can look at the analog shrink thinking and ask does a version of it hold, and you could define that that's what you mean by ETH in that context. But I'm sort of puzzled as to what
Yes.
I perfectly well understand ETH. The question of ETH in the sense many particle non-interacting. Right, you still have L particles, right, but they're non-interacting.
Yes.
I don't really understand what it means conceptually. In a more conventional sense.
Yes.
It's a statement of lack of understanding in my part.
Thank you for this question because you now allowed me to extend for 2 more minutes. So I can tell you, I can give you the answer from my personal experience. So we studied single particle ETH in Anderson model, in well-known Anderson insulating problem, which is known for 60 years. We studied that. We found that that is valid in the Anderson model on the delocalized site, on the chaotic site. We thought it's an expected result. It is expected, but so far nobody studied in the Anderson model there. Yes, yes, yes. Of course, that's a direct consequence of Berry's conjecture. Right. Now, and then we struggled exactly with this question for 2 years. And then we found one possible answer. We found one striking consequence that I think was not known before. If this is valid, you can then prove that the observables in many body states of a non-interacting system will equilibrate. Well, if this is not valid, your observables, few body observables, in many body states of non-interacting systems will never equilibrate, will oscillate forever. So this is now something that is non-trivial in the sense that in interacting systems, I said, if ETH is valid, then automatically you will thermalize and you will equilibrate in the sense that fluctuations of the temporal fluctuations above the long time average will go to 0. And even more brutally, I didn't highlight it, they will go exponentially fast to 0. Now here in non-interacting systems, nothing goes exponentially to 0, but you have 2 scenarios. Either observables equilibrate, so that the time fluctuations about the long time average go to 0, or not. And that is actually, this property is linked to the validity of these ansatz.
Basically, standard regime of an model. You know, the anode.
Exactly. Exactly.
The anode.
Exactly. So you have so if you're in the delocalized or in the diffusive regime of the Anderson model, you do quantum quench, you have observables, they always go to the generalized Gibbs ensemble that I will discuss tomorrow. They never thermalize, but in terms of equilibration, in the diffusive regime of the Anderson model, fluctuations about time average go to 0 because of that. If that is not valid, that they will not equilibrate. Yeah.
As opposed to you.
Yes. Yeah. Exactly. And that has a consequence that it's quite non-trivial, even though it's very simple. That Anderson model in the delocalized regime has diffusive transport, but still it's non-interacting, right? So non-interacting means that it doesn't thermalize. That in principle you need generalized Gibbs ensemble, but it does equilibrate. Yes.
like let's consider RMT and that's it. And then like
Yes,
let's just say that single particles just here in space of time in which we don't know instead of that.
Yes.
Well, it's like in the Intec case, you had some restriction on the operators. It has to be few body operators.
yes.
Is there a restriction on these operators here also that they
Yeah.
have to be low?
Yeah. So here is just essentially one body, right? Because then because if two bodies, then because you have Wick's theorem, and then you can express it in terms of products of single body. So here I just not only few body, I just restrict myself to one body observable.
They have to have some restriction like whatever.
Local and physically relevant space. So here quasi-momentum occupation is still a good observable. Yeah. So okay, let me finish now with this statement that if this is valid, then the system we call single particle chaotic. There is single particle chaos. If violated, then there is single particle localization. So single particle localization, what is that? Of course, that's, I just want to be formal. I want to distinguish it from many body localization. Single particle localization is something that naturally occurs in Anderson model when you have Anderson insulator. Anderson insulator is a manifestation of single particle localization. Now in this language also I have to be strict in this sense. Also translationally invariant limit of free particles, which is essentially plane waves, is also single particle localization, is single particle localization in quasi-momentum space. Okay, that, of course, that's just a language. You can say, well, it's trivial. Of course, if I have non-interacting particles in a without disorder, that's trivial. Yeah, it's trivial. I agree. But just in this language, that course, I would call it single particle localization in quasi-momentum space. And of course, then observables related to quasi-momentum space will violate that. Okay. This statement is basis independent, but here what I want to highlight is that what are the observables that violate single particle ETH if we have single particle localization. So in the Anderson model, when you have real space localization, when you have Anderson insulator, the observables that violate single particle ETH are related to real space properties. So density, local site occupations, local hop, local kinetic energy. They violate that. If you get rid of disorder, if you go to transition invariant free fermions, you have localization in quasi-momentum space, then observables that violate that are related to quasi-momentum space occupation. So for example, if you have a box with open boundary conditions, so that quasi-momentum occupation are not really eigenmodes of the system, but if you calculate for quasi-momentum occupation, this ansatz, it's violated clearly. Single particle ETH is not valid.
Disorder and go to the diffusive regime, so that's the only difference, right? So
yes, if you go to if you're in the diffusive regime, then a spectrostatistic is RMT-like. You can say the system is chaotic, and single particle ETH is satisfied for all observables.
You commented also about the absence of degeneracy. So
yes.
For quasi-degenerate states works also, like for minimal.
How we define quasi-degenerate?
Maybe some kind of a minimal perturbation in the initial state that can break the degeneracy of the system, like perturbation of the fields.
Typically, degeneracies emerge because of some symmetry reasons. Now, of course, I haven't yet used the word symmetry here, so I avoided that successfully. Yes, and this always requires some more care. It requires some more considerations, requires actually the ETH to be looked at in a given symmetry sectors. You can also then study what happens when for the observables that couple different symmetry sectors, and then that can further complicate. Yes. Okay, I think I need to stop,
Yeah.
right? Okay, so thank you for patience. Let's continue tomorrow. Yes.
Let's resume at 4:40 for the last talk. Okay.
Good.